Welcome to the solutions to the Regents Physics Momentum Problem Set, problems number 8 and 9. Let's go ahead and get ahead and get started here with number 8. A cue ball travels across the pool table and collides with a stationary 8 ball. The two balls have equal mass. After the collision, the cue ball is at rest. What must be true regarding the speed of the 8 ball? I think intuitively we understand and maybe draw the conclusion that the 8 ball would have the same speed that the cue ball originally had. They're just trading since they have equal mass. But let's show this with appropriate physics. We start with a before and after diagram of our situation. Before the collision, we have the mass of the cue ball that has initial velocity VI as labeled in the diagram, and our 8 ball has an initial velocity of 0. It was stationary as mentioned up here in our problem description. After collision, we're told that the mass of the cue ball is at rest, so we have our mass of cue ball labeled with a final velocity of 0, and our 8 ball travels off with velocity we'll label at the moment VF. We're also told in the beginning of the problem that the mass of the cue ball is equal to the mass of the 8 ball. The two balls have equal mass. Setting up our conservation of momentum statement, we start with P before equals P after. And you can see it's important that your before diagram and your after diagram relate directly to your conservation of momentum statement, because the next thing you're going to do is put down the object or objects that have momentum before collision and after collision in appropriate form here. Before collision, the only object that had momentum was the cue ball because it was the only one that was moving. So its momentum would be mass of the cue ball times its initial velocity. After collision, the only object that has momentum is the 8 ball because it's the only one that's moving. So we express its momentum as mass of the 8 ball times its final velocity. Well, given the fact that the mass of the cue ball equals mass of the 8 ball, our masses cancel in our equation, and therefore we draw the conclusion that the initial velocity of the cue ball is the same as the final velocity of the 8 ball. And there it is shown with physics. This is a nice lead-in to our next question. We apply this to a different scenario. Let's go ahead and read it. We have a 95 kilogram fullback mass running at 8.2 meters per second. Initial velocity, collides in midair with a 128 kilogram defensive tackle, is mass, moving in the opposite direction. So his initial velocity is opposite of the 8.2. Both players end up with 0 speed, so the final velocity of both players is 0. Draw before and after diagram of this situation. What is the velocity of the defensive tackle before collision? So we're trying to find VI of the defensive tackle. As requested, we start with a before and after diagram. Beforehand, we have the smaller fullback of 95 kilograms. We'll say is moving in this direction at 8.2 meters per second. We'll say to the right. And we're told the 128 kilogram defensive tackle moving to the left at an initial velocity we're trying to find. After, they become an entangled mass of a combined 223 kilograms, adding the two together, with no velocity. They end up with 0 speed on the collision. This leads into our P before equals P after conservation of momentum statement. Beforehand, what are the only objects, if any, that have momentum? And the answer is both. Are they together? No, they're separate. So we have separate momentum equations for the two individuals before collision. We have the fullback's mass times his initial velocity plus the defensive tackle's mass times his initial velocity. What objects, if any, have momentum after the collision? The answer is 0, because both of them combined together and had 0 speed. So no momentum after. Now we just need to solve. Clearly what you would do is you would take this momentum, this product, I want you to determine what it is, and subtract it over to the other side, and then you would divide by the 128 to solve for VI. This would give you an initial velocity of negative 6.1 meters per second. This makes sense because the defensive tackle was moving in the opposite direction as our 8.2 meter per second fullback. So his velocity should be negative. All right, that'll do it for number 8 and 9. More practice with conservation momentum as we do problem 10 in class tomorrow.